Programming instructors often conduct in-class exercises to help them identify students that are falling behind and surface students' misconceptions. However, monitoring students' progress during exercises is difficult, particularly for large classes. First of all, for students who have correct solutions, they can have different approaches in their code, including various APIs and logics. As these students are writing toward a final solution, they may be running into a variety of barriers, including type errors, name errors, syntax errors, or even have valid code but not pass the unit test. To identify misconceptions among students, only looking at the error messages is not enough. Instructors need to read their code in detail to gain more insight into their intentions. In addition to that, for students who have incorrect solutions, they may be at different stages of solving a problem. Some students are close to a final solution, needing only minor changes to their code, while others have no clue how to begin. What if checking where a student is on a programming exercise could be as easy as seeing where they are on the map? On the map, if we know a person's starting point, destination, and location, we can easily determine how close they are to their destination. With real-time updates, we could also determine if they are progressing to their destination or if they might be lost. We introduced VizProg, a system that explicitly encodes human understandable meaning to the space and that can work in real time at a keystroke level. VizProg's user interface consists of three main panels: the overall class progress 2D map view, a solution-centered view, and a progress detailed view. In the 2D map, student status is represented as a position. Large colored dots represent where students are. Blue dots represent students who have solved the problem successfully, while orange dots represent students who have not yet found a solution. The small gray dots represent versions of code that students have tried but have since moved on from. The gray lines represent trajectories between two consecutive versions of code. The 2D Euclidean distances encode similarities in students' code. The vertical positions encode how students approach the exercise. The horizontal position represents how close students are to a correct solution. Instructors will see students' positions changing on the map as they type. In this example, the programming problem is to create a list of numbers ranging from 0 to 40 and calculate the summation of the list. As student A, B, and C working toward the solution, their dots are moving from left to right. After a while, student A comes up with the correct solution using approach 8, and student C gets very close to approach 24, while student B is still very far away from a successful solution. VizProg allows the instructor to inspect the submissions from all the students who arrived at the same solution by clicking a solution. The list contains three main sections: statistics related to the solution, a list of IDs of students who are close to the solution, and a list of submissions made by these students. Instructors can click the student ID to view the trajectory and code history of a specific student. The progress detailed view displays all the submissions made by the student throughout the history of the exercise. Instructor can also navigate students' progress at different granularities. To examine the progress of groups, instructors can crop a region on the 2D map to see the submissions only within that region. To assist users in identifying common misconceptions, submissions are listed by error type frequency in descending order. By resizing the overlay or dragging the overlay on the 2D map, the user can view real-time updates on the progress detailed view of the selected region. For individual progress, users can either search by student ID or click a student ID on the solution-centered view. This student's progress will also be represented by a trajectory line on the 2D map. We ran a within-subject study with 16 participants to evaluate the effectiveness of VizProg. The results showed that users understand misconceptions more accurately and faster than the baseline system. Furthermore, participants reported that VizProg provides richer and more comprehensive information for identifying important student behaviors. Based on what we learned from the study, VizProg points to a direction that helps instructors improve the live learning experience by better understanding students' mental models and provide tailored feedback at scale.